Hello there, welcome back to chapter 17. We have gone through so far most of the basics of this chapter. Okay, now we all need to do is to apply everything we have learned. So before this, we have looked at drawing, defining, calculating forces and field strength. Previous video we looked at work done, extending our knowledge in chapter 6 and chapter 5. The final bit that we'll be looking at in the last few series of videos, the short ones, are describing the effects when a particle is in a field. Yeah, we know there's a force, yes, we know there's the field, but we know what happens to that particle when it's moving. Does it accelerate? Does it slow down? Does it move somewhere else or curve somewhere else? So there are three different groups or effects that can happen on a particle. We'll be looking at the first one today, and that is for a particle suspended in equilibrium. Equilibrium. That name is very, very familiar. Where did we see equilibrium before? Equilibrium comes from chapter 5. Basically, it means no net force on the particle. No net force is what it means in equilibrium. So net force is 0. We also remember in chapter 5, we also talk about no net torque. But in this case, the particles are just particles. So you don't need to worry about the net torque part. But just so you know, equilibrium means no net force. Means if you have a particle, you have, let's say, some force acting this way, you have another force in the other directions. Same magnitude. Therefore, F1 plus F2 is 0. That's what we call net force. So that's the idea of equilibrium. Just a quick refresher. Today we're going to look at just 3 different examples of equilibrium, and the questions will pretty much repeat themselves in the past years. So if you can understand the basics behind this, that would be great. Okay, so let's switch over to our OneNote and start off there. Okay, that's the work done from previous unit of how do you know if there's work done or not, how to calculate it based on change in potential. But today we're going to look at equilibrium. Let me zoom in a little bit to make it bigger. Okay, what does it mean suspended? Suspended, well, you can think of suspended as hanging there. So some particle is hanging there, but what does that mean? Okay, here, let me draw a picture for you. This is on back in the beginning, page 2 of the handout if you're taking notes, or if not, you can just draw your own. Okay, let's say I have 2 plates. My good old 2 plates. 1, 2. Imagine they're straight plates. And I need to, these plates can't really generate electric field unless I do something. What do I need to do to a plate so that it has an electric field come out? So what should I add there? Well, I need to add potential difference, so I need to connect to a circuit. Okay, so let's say I connect the top part to, connect to 800 volts. 800 volts apply. Then the bottom plate, and let's just make this 800 volts connect to ground. Ground means 0. Then the bottom plate, I connect to another supply, which is, let's choose 200 volts. Power supply. And that one also connect to ground. So that means the potential difference will be 800 minus 200, and that is the potential difference between the first plate and the second plate. Okay, now that we have a potential difference, we have an electric field now. Yay. So electric field is going to look something like, which one is higher potential? Top one. High potential, lower potential. So you can draw electric field lines looks something like that. Straight ones. Straight electric field lines. Okay, I won't draw all of them, but you get the idea. There will be electric field lines going from top to bottom. Because up here is our 800 volt plate. Down here is 200 volt plate. So sliding downhill, remember we talked about that? The positive charge will slide down. Now, let's say I put a charge in between these plates. And I say, let's put it a negative charge. There is a chance that this charge will just float up there and just never fall down. And why is that? Because there's a way to adjust this so that it becomes an equilibrium. Okay, so what is the electric field strength? here. Well, we can calculate that. But this charge will experience a force in which direction? Normally, you will say, oh, if it's positive, you follow direction of arrow. But no. This one, we are looking at a rebel charge, a negative. So the force will be in the opposite direction, Fe. That's where it would normally go lah. So the moment you turn on power, bzz, the charge will go up. Bzz. Normally that is the case for small particles like electrons. But if this charge is so fat, so heavy, such that it also have a weight, so then you will have something else called the weight. If your weight is, we call it W, or gravitational force, pulling the charge downwards. So if you can adjust it such in a way that the downwards gravitational force balances the upwards electric force, then it's an equilibrium already. Yay! Okay, that's what we call in equilibrium. So for this negatively charged example, negatively charged object, usually it's something very big like an oil drop. So particle, object, oil drop lah, let's say oil drop. Because electrons are too small, their mass is negligible. Then in this case, you can have a net force of 0 because your electric force upwards equals to the downwards electric force in magnitude. So no net force. Very nice. And this is the up, this is the down. Okay, so far so good. Now, what you could do further if they ask you all kinds of questions about this equilibrium idea is you just plug in all the equations you know. F is what? QE, right? So QE. And then gravitational force is what? Mg. Oh, so Mg. So you can do stuff like this to expand the equation and get all kinds of equations based on this main one. But this is one example of how you can expand this idea of equilibrium to form other equations like that. Now, some of you may be wondering, Miss, so actually what forces are acting on these particles when they're electric fields? Great question. What forces are actually there? Well, firstly, you have electric force. Because if you're in an electric field and you're charged, then you will experience electric force. That's for sure. Then, if you are heavy enough, you may experience gravitational force. So if your mass is not negligible. So for electrons and protons, those mass is like so small they're negligible, so we don't consider electrons and protons to experience such a big gravitational force. But if it's oil drops like this one, or a charged tennis ball, a charged ping pong ball, all these kind of other objects where the mass is not negligible, then yes, you have to consider gravitational force. Some people will also ask, Miss, is there drag force? These experiments that we do are usually done in vacuums. So here, vacuum. Means in that whole area with the electric field, there will be no air resistance in there. So we don't consider drag force. No, there's no drag force inside these experiments. So mainly electric force, if it's heavy enough, they will talk about gravitational force and you'll see them, especially when they talk about oil drops. So remember, oil drop, when you see oil drop means they have some kind of weight also balancing out. Okay, so let's look at some examples based on this idea of suspended in equilibrium. Let's turn over to page 10 to look at the first one. Well, turn over means scroll over for me here, if I can find it. So give me a moment to scroll down to page 10. 6, 7, 8, 9, 10. This one. So this first one is a pass here. Oh, that's kind of fuzzy. Okay. So this is MJ15 P12, question number 30. I want you to try pause this video for a little bit. Try to apply what we just talked about in equilibrium to see if you can figure out how can you find some equation to solve this. Remember I talked about the equation? Okay. So pause it, try out first, see if you can somehow manipulate all those variables to get the equation that they want for equilibrium. Okay, let's take a look. A charge, oil drop. Oh, they talk about oil drop. Remember we say oil drop, the mass is quite big one. Okay, so we have mass M with n excess electron is held stationary in the uniform field between two horizontal plates separated by distance d. Whew, let's draw it out to see what's happening. So first you will have an oil drop, pretty big one, some mass m which will cause it to have gravitational force, mg, and also it will experience an electric force. Well, it's held stationary. Is it positive or negative? Well, you see this side, the long one means this side is positive, this is negative. So this is the positive plate and this is the negative plate. So that means it is going upwards, or it's trying to go upwards, experiencing an attraction towards the positive plate. Means it has to be negative charge. And there's many negative charge there because it has n excess electron. If you have 1 electron, then 1 negative charge. If you have 500 electron, then 500 negative charge. Okay? So they're trying to find the value of n here. Wow, very strange. Value of n. So here you usually will say the electric force experience is QE. Right? Okay. Now, yes, two separation by D. Voltage is V. Well, I guess potential difference here is V. Elementary charge is E. Oh, interesting word. What is elementary charge? Elementary charge basically means the fundamental unit, the charge of an electron, which is, what we looked at, 1.6 times 10 to the negative 19 coulombs. That is what we call E lah. Electron charge or also proton charge. Now what? Okay, so now previously we say, okay, so if it's held stationary, means net force is 0. Means the upwards QE equals to the downwards mg. Yay, okay, problem solved already. Wait. We want n. How do we get n into the picture? N is the number of electrons, right? So what we can do is, how do you find the charge of this oil drop? What is Q? Question mark. Well, Q here, the charge of that whole oil drop will be the number of electrons times the charge of 1 electron. Okay, I repeat, N is how many electrons are there times the charge of 1 electron. Okay, so this is the key to finish up this question. So then we know Q is Ne, so we have Ne equals to mg. Answers don't have big E inside. Means we need to get rid of the E also. What else do I know about E? Oh, E is related to the potential difference against the separation. So let's sub that in. So then you have Ne V over D times mg. Woo! Some morphing equations here. And now you need to find N. So let's rearrange all these variables here. So N equals to, firstly mg, D goes up, EV goes down there. So mgd over EV, that is what we're looking for. This thing. So this is the answer that we're looking for, B. A lot of people, they forgot, they're not sure how to deal with this N, how to get this involved. But remember this thing. Total charge of this object is how many electrons are there inside that oil drop times the unit of charge for 1 oil drop. And then from there on, all we did is, okay, this is condition for equilibrium because they told us it's held stationary. And then we proceed to plug in all the equations to get what we finally want. So this is one example of an algebraic question, how you can solve it when they give you equations to do like this. Let's look at another one. On page 14, this one, more of a word equation. Let's see. Scroll down to page 14. I think it's somewhere there. There, I skipped over here. Skip all the scrolling. Hey, internet very slow. Never mind. So this is on page 14, a past year question that is related to oil drop suspended in space. Okay, here we have a constant potential difference between two horizontal plates. Okay, so we know there's a change in potential here. A charged oil drop is held stationary. Ooh, stationary. So whenever you see the keyword stationary, it's basically talking about equilibrium. Equilibrium or net force acting on this particle is 0. And it's talking about oil droplets too, so you know that makes sense. Oil droplet charge. Okay. So as some of the oil evaporates, the droplet lose mass and start to accelerate. But its charge is the same. Wow, that's interesting. In which direction does the drop accelerate? So where does it accelerate? And what change do you need to do to the separation of plates to stop the acceleration? Let's look at the acceleration part first. So if I redraw this particle, if it's held at equilibrium, then it means the upward electric force is equal to the downwards gravitational force, right? But then, as it evaporates, it loses mass. So your mass is decreasing. Uh-oh. Mass decreasing means your weight of this particle or this Fg, gravitational force, is going to decrease as well. So what's going to happen is your electric force is still the same because Q times E. E is not changing, yet Q is the charge of this thing. The charge remains constant, they told us. So what's changing is your downwards gravitational force has become smaller, decreased. So as you're losing mass, it's decreasing. So then where is the net force pointing now? Which one is bigger? Now as your Fg gets smaller and smaller, your net force will be upwards. So then, if the net force is upwards, means it will start to accelerate upwards. So as it evaporates, the particle will slowly go up. Go up, go up, go up. Okay? So that's the first part. Directional acceleration, we can look through the answers. We'll say downwards, upwards, downwards, upwards. We know it's upwards. Okay, so this one's out. Now, separation of the plates. What did they want us to do again? In which direction does the droplet accelerate? Okay, we did that. And what change needs to be made to the separation of the plates to stop this acceleration? Well, we have a problem here. If we want to stop acceleration, we need to decrease our electric force so that it can be balanced again. So electric force also becomes smaller. Then you also balance the smaller gravitational force. So we need to decrease electric force, number one. To do that, what can we do? Remember, F equals to Q times E. We can't change the charge Q because it's constant. But what we could do is, we can decrease the electric field strength. Okay. Is there a choice to do that? Oh no, they want separation of the plates. Okay, so we need to think a step further. How do you decrease field strength? Need to decrease electric field strength. So what can we do? You think more, what other formulas are there? How does E relate to separation of the plates? Separation of the plates. Okay, so E depends on potential difference and D. There are two ways we can decrease E now. So we want to decrease E, means we either decrease V, but that's not a choice. So we cannot decrease V. So we can change D. So you want to decrease E means you have to increase D. Because D is at the bottom, so it's an inverse relationship. Okay, and let's rewrite here. E is proportional to 1 over D. So if this one decrease, means this one has to increase. So we need to increase the separation of the plate to make the electric field weaker. Okay, so here, we need to increase to make E weaker in order to make our electric force smaller, to match the shrinking gravitational force. And of course, this one upwards because we looked at the equilibrium thing. So just remember, this question might seem a little strange because there's no values for you to calculate it per se. But remember to think through it step by step. Oh, I need to reduce this. So to reduce this, I need this. To do this, I need this. To do this, I need this. And then you write out your reasoning properly and then cancel out choices that are not correct. Okay? So if you have any questions about this one, just throw it in the questions channel back in our Teams group and make sure you get these basics ready. Because next up, we're going to look at a calculation question. This one, dun, 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 is a paper 2 structure question on page 22. Let's go and see what that is. Okay, here's page 22. By the way, there's a typo. This is not MJ14 P22. This one on page 22 is supposed to be ON14. So let your friends know if they are doing it and they're like, oh, why cannot find the answer, the mark scheme one. Just let them know there's a typo to fix. Okay, so let's take a look at page 22. Now, how do you do this thing? If you are just watching the video and watch me do like that, oh, that's not going to work, friends. You have to do it along with me. Or even better, you pause the video, you take, wait, how many marks is this thing? Let me see, 2, 3, 4, 5, 6, 7, 8, 9. 9 marks. So that means you should take about 12 minutes or so. This is the recommended way to do this. So take 12 minutes, pause the video to try this whole question first. Never mind if you don't know how to do. You try your best to go through it. If you're stuck, it's okay. Take some time to, our brains take time to think, right? You can't just expect to immediately know how to do certain things. So take 12 minutes to try this. Or if you really are in a rush, then you can do it along with me. But make sure you try to do it along with me, because then we'll mark through it. Okay, so go try it out first. And we'll see how we can solve this question. So define electric field strength is the first part. Oftentimes in structure question, they will start off with a define question like this. They ask you, explain this, state Newton's second law, define electric field strength. So you have to remember what is electric field strength. So one way you can say is, electric field strength is, I skip the fun part, force per unit charge. This is one of the basic ideas you can say, force per unit charge. But here's something important. This thing is best to add. You want to say force per unit positive. You can say positive charge or positive test charge. This test one optional lah. But this is the best way. I'm going to mention positive charge because the force, we say, oh, here you experience a force. That's usually we're looking at positive charge, where the direction of the force. Because if you do negative charge, it's in a different direction already. Okay, so we want to look at positive test charge, and that's very important because in some past years, they will look for that word positive. They will actually underline it. Underline means you must see that word in the marks. The marking underline means you must have that word in your sentence only. They give you your B1 mark. Okay. Some other past years are more relaxed depending on the year one. Sometimes they say non-need positive also can. So, best way to make sure you have that positive charge in your sentence, then only can lah. Then you will get your 1 mark there. Okay? Now, next part here. A sphere has, wow, this is a very interesting, suddenly electric field, how come suddenly got density, all this thing one? Well, these are cross topic. A sphere has radius 1.2 and density 930. Show that the weight is that. Whenever you see show questions, it means the answer is already given to you. They just want you to show how you got the answer. Okay, so in this case, if you have no idea how to do this, you forgot the formula for density or mass, you can actually just skip B, go on to C, but remember to use the value that they gave to you. Yeah, you can just take that value, continue, and then solve. But anyway, since we're doing this, I'll go through very quickly. We have radius, density, we want to find weight. So you need to remember, density is mass divided by volume. A sphere, oh right, sphere. So we need to find the volume of a sphere given that the radius R is that value. Okay, so if I rearrange this, it'll be, we want to find the mass to find the weight later. That will be density times V. Density is given to us, 930. check my units, kgm negative 3. Volume. What's the volume of a sphere? This one must memorize. Volume of a sphere is 4 over 3 pi r cube. So you need to write 4 over 3 pi, let me use another bracket for this, r cube. So 1.2 times 10 to the negative 6 meters cube. Then you get your kg. Well, some of you may do this in one step, but I'm breaking it down. So 6.73 times 10 to the 15 kg. That's the mass of this tiny, tiny little sphere. Here, if you kind of show this density equation, or if you didn't write that, you did this step, the calculation part, that's okay. You get a C1 mark, and then, is there A1 mark here? No, there's no A1 mark here. Whoops. Hang on there. Wait for the final answer. So then you need to find your weight, which is basically a gravitational force, which is m times g. So you just take your previous m times 9.81. I'm lazy to write it out. I'll just write that m times 9.81, not enough space already. Equals to, you should get a very, very small weight as well. That should be about 6.6 times 10 to the negative 14 newtons. There we go. So we have a C1. And finally, if you write everything down, then you get your final M1 mark here. M for method. To show that, oh, okay, then you found mass and then you found weight. That is, if you check, oh, it matches, then you're good. Shown. Therefore, it is shown how you got the answer. Then you go on to C. Okay, this is where the electric stuff starts happening. So you have two horizontal metal plates apart in a vacuum. A potential difference of 1.9 kilovolts. Okay, so up there is 1.9. This symbol down here means ground. This thing. Ground basically means 0 lah. Consider it like 0. And then, okay, so that's the picture. Electric field, uniform electric field is produced. Uniform is important because only for uniform, then you can only use this equation. This equation is only for uniform field. Okay, then the sphere is held stationary. Now, when you see the word stationary or at rest, that means we're talking about equilibrium between the plates. Calculate the electric field strength between the plates. Ooh, interesting. So first things first, if you're not sure where the field lines are, just draw some lah. Then you can have an idea. Oh, the straight field lines are pointing from top to bottom because here is high potential. Here is low or basically 0 potential lah. Okay, up there is 1.9, very high. And if it's held stationary, okay, means that this thing has some weight, Fg, and it's also experiencing our electric force upwards. Electric force depends on other stuff. Okay, but here we only want electric field strength. So I need to write electric field strength is the potential difference over the separation. What is that given to us? Oh, it is given to us. 1.9 kilovolts, 10 to the power 3 is kilovolts, minus, at the bottom is 0, okay, so the 0. These are all in volts. Let's write the units. Good practice. Divide by separation distance, that's 14 millimeters, so 14 milli, the milli means negative 3, and this is in meters. So you get a pretty big number. I calculate for you. You should get about 135714 volts per meter. And final answer, if you ever see like these dotted lines, this is where you want to write your final reported answer. Now, to make the examiner's life a little bit easier, you can usually round off to 2 or 3 SF. Meaning, firstly, let me just change this to standard form lah. Well, let me just do it down there. Standard form, usually you have a digit and then a decimal point. So 1, 2, 3, 4, 5 dot. So I can write 1.36 times 10 to the 1, 2, 3, 4, 5, 10 to the 5. This is one way I can report it in 3 SF. This will make your examiner's life much easier, and they actually prefer either 2 or 3 SF when you write your answer in this dotted line. If you want 2 SF, can also allow you 1.4 times 10 to the 5. Both is okay. Alright, so that's how you can Find electric field strength. Where do the marks come from? Take a guess. First one comes from the formula. If you show that you knew how to use V over D, either here or here, that's a C1, C for compensatory. Then if your final answer is correct, that's your A1 mark. A for accuracy. Ta-da! Not too bad so far, not too bad. So we've found the electric field. Now we need to find the magnitude of the charge. Okay, this is where I gotta scroll over a bit. Calculate the magnitude of the charge on S. Magnitude of the charge. Why do we need to know the magnitude of the charge? How do we do that? What does that even mean? Don't panic. Magnitude of charge. When you see the word charge, that means they're asking you what is Q on S. Do we know Q? What equations has Q in it? F. Right, let's write that down first. F, electric force, equals to QE. Hey, we do know what E is. Let's do that. But we don't know what F is, because if you just do this, Q equals to, what's E? E is, where was the E? 1.36 times 10 to the 5. Then you don't have enough information, you can't find Q. Sad face. But you have to remember, all these questions are connected from part A to part B. Are we in B now? I lost track. Oh, part C already. Okay. They're all connected. So you need to remember, we talk about thing in equilibrium. So it has a Fe, which is the same magnitude as the gravitational force, which we found earlier, the weight of S in part B, which is 6.6 times 10 to the negative 14 Newton. Oh, so we do have enough information. So because Fe is the same as Fg, which is 6.6, then you can do this nice calculation. You say Fe equals to Fg, so therefore 6.6 times 10 to the negative 14 equals to Q, what we're trying to find, times the electric field strength that we found in the earlier question. So that'll be I'll just use 1.36 times 10 to the 5. Yeah, then we can find our Q. What I did in my calculation is, instead of using 1.36, I used more decimal points. That's okay if you use more, just not too little. In fact, more will be more accurate. I use 1.357, my original calculation. So I'll get about 4.86 times 10 to the negative 19 coulombs. But in my final answer in the dotted line, I can round it off to 2 SF or so. So I'll say 4.9 times 10 to the negative 19. So here they allow 4.9, they allow 4.86. They also allow, what's the other one? I lost track of my thoughts. 4.7 times 10 to the negative 19 if you use a rounded value of your E. If you use 1.4, you will have this. But you must show you're working if you use E equals to 1.4 times 10 to the 5. It's a by the way note. So how many marks is this thing? 2 marks, you can guess. 2 marks, probably 1 for equation, 1 for final answer. And that is correct. The first mark comes from you rearranging this equation. Fe equals to Fg equals to QE. And then you try to calculate it either here or here. You show that you knew how to do that. That's okay. Then if you get your final accuracy mark, you manage to get this or any of the other accepted values, 4.9, 4.86 or 4.7. If you use the other one, then that's 2 marks for you. Yay! So this is how you can do calculations. The last one. Okay. So each structured question comes roughly in this pattern. First part, they ask you to state a definition. Maybe they ask you to show something. They ask you to calculate some stuff. And the last part, they will either ask you to draw a graph or explain, like this part 3 here. So they say, explain this, explain that, describe, explain, things like that. So this is how each structured question is shaped like. They will ask different skills in physics. And this is the last one. So the magnitude is increased. Explain why S accelerate to the top plate. Wow. The magnitude of PD, what is that? PD basically means potential difference. So V is increase. And then you need to explain why S will accelerate upwards. Okay, in case we forget the picture, let's zoom out a little bit and see. Come on, load. Lost my thing. Anyway, there it is. So here we have the good old plate. If you suddenly crank this up to bigger value, what's going to increase? So electric field strength is V over D. If you crank up your potential difference, your electric field strength is going to get really big, which means if your electric field strength get big, your force is going to get really, really, really big. So this Fe here is going to change once you change your V. So how can we write that out? Well, you want to tell the story as wholesomely as you can. So the first step, perhaps, you could say something like this. When you crank up the potential difference, your electric force will increase. Well, you say increases. Electric force, because of, you can say electric field strength increase, so electric force increase. But anyway, electric force increases to be more than the weight now. This part you can mention to be more than the weight. If I draw a picture, it looks something like this. You have a charge, weight is still the same, but now, wow, your electric force become much bigger already because you increase your V. So once this thing happens, your net force is going to be upwards, which means you're going to accelerate up. And that's what they wanted to talk about, right? They explain why accelerate. Okay. So then you want to say the resultant force or net force. Some people prefer different things. The resultant force upwards will be the resultant on net, there will be a resultant on net force upwards, because you can say the charge is negative. Because if it's positive, your electric force will be pointing in different directions. So it's good to say what is your charge and where is it pointing. Because notice they didn't tell us, they didn't say whether your charge is positive or negative. The only one, they say magnitude lah, find other thing. So actually, they didn't tell us and we kind of assumed it wisely. So we must mention it here also. Net force upwards, charge negative, blah, 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 things like that. Okay. The mark scheme says, firstly, you want to talk about, yes, electric force increases, or electric must mention, underline it. So that's one B1 mark there. Then if you want to talk about the net force upwards, that is the second B1 mark. It's the best if you can also mention the charge is negative, so electric force is upwards and net force is upwards. Okay? So that's a nice length kind of question on calculating the electric force for this kind of object in stationary, floating, at rest, all kinds of stuff. Usually only for oil drops, because electrons, protons, we say their mass are negligible. So the weight we just say is too small compared to their charge. So no more. Okay, so that was all I wanted to show you for today. Just this bit on how to practice through questions related to things suspended in equilibrium. In the next videos or so, we'll be looking at fun stuff where now the charge is flying through the electric fields. And then you will start to have more kinematics coming in as well. Kinematics, energy, work done, things like that. But that's all for today. I'll see you in the next video when we look at the last few applications of charges moving in electric fields.